All right. So today we're gonna be having the some of the issue about the exams. So I graded on Thursday and Wednesday, whatever it is. So I feel like there was a couple of people who actually did not put the files or convert it to the PDF file or the image file. So there were some image file that I cannot read. Um, the tell HEIC, those are basically the file that I cannot read unless I have to use the phone, but I don't really quite feel comfortable to read the exam on the phone. So make sure that we convert it to the PDF or the Word files or maybe the image file in terms of the GPG, I'm sorry, JPG or PNG. So those files I can read. So so apologize for the noises from the AC and then also a very poor unstable connection that I have. The Spectrum they're gonna come today to fix them. So there was uh, some headache that we have right there. But anyhow, again, that we're gonna cover lecture 9 today and finish lecture 10. So on um, when we come back on Thursday, so that would be the last lecture. So that will be on June 25th. We're gonna be covering I would say we're gonna be covering the last lecture for induction, the proof for induction, and that's pretty much it. So once we come back on um, June 30. So that will be the date that we're going to use to review for the exam. And then the final exam will be on July 2nd. Okay. So again, that we got to finish it. We got to finish the lecture by this Thursday. And then we try to have and finish the final exam review on June 30. So on that day, I do not cover anything new, but I will basically go over some of the material that we need to study. I'm going to put some important marks on it. And then once we come back on July 2nd, we're not going to meet and see each other in Zoom. We're basically going to have the exam taken on Blackboard. So that will be the thing that we're gonna have to take the exam on that day. So after July 2nd, we're not gonna meet each other again. We're going to have if you want to uh, get some clarifications on your grade, you can also email me or you can see me on Zoom. This is the meeting that we can click on. So this is the Zoom office hour meeting. So we started right after that, but you have to email me before because I usually do not start. You need to let me know that you will be there in advance, maybe 20 minutes in advance, so that I can set up the meeting for us. Okay, I actually set them up on Zoom, but I do not start unless there was somebody who told me that I was gonna be going there. So the grade should be you guys still have the grade for that. I'm gonna grade it very soon, but the fact is I want you guys to be able to finish it and and have the solution posted, and that is the most important thing. Usually I grade at the end of the semester, but this time I will grade a little bit sooner so you can see the procedure that I grade the homework problem. Remember that the homework is part of your grade. It's not just like check or no check. It's great. It's like, 5 out of 10, 7 out of 10, 8 out of 10, 9 out of 10, 10 out of 10 on that part. I would say the exam grade was up, but I emailed some people who did not finish or the upload. For example, Daniel, you forgot to give me the grade for question number 9 and question number 10. So making sure that you have to send. I sent you an email, but I got no response. For people who I send an email and receive no response, I just I might, take away 2 questions that I did not see the solution on it. All right. So making sure that you respond in email as well. And I also noticed that there was some file that I cannot read, and also email that person again, but I received no response. Again, you need to email me on that part. So anyhow, again, that I do not really want to take away the point of the question that you leave blank, or maybe you forgot to upload. But please try to do so, because on a final exam, I just grade what I have. I do not ask you, hey, did you upload question number 5 or question number 2? I think I posted, right? Did I? You can check it. So how can I get the videos anyway? So you can go to um where's the videos? I believe I think I posted. Yeah, right there. So you can click here, right? So everybody sees the click here for YouTube channel. So you click on it, and there will be take them now. So there will be the channel that you can have the thing. So it's not really like a long videos, but it's gonna be very, very you know a good contribution for us before the exam. Um, so any other question? Any other concern about the final exam? Remember that the final exam will be actually next week, right? Next Thursday. So you have uh, around 9 days left. And Thursday will be the last lecture, and next Tuesday will be the exam review. Okay. So did I clear your questions up, or did I clear up any confusion that you have? Again, that for those of you that you don't see the grade, make sure that you check the email. You just join, so um, I recommend you watch the video again. I'm just kidding. I don't want repeating myself. I'm just kidding for that. So the next Thursday will be the final exam review. Where I'm sorry, next Thursday will be the final exam. I apologize. So next Tuesday will be the final exam review that I'm gonna be going over most of the questions this Thursday, not next Thursday, this Thursday, right? So this Thursday, June 25th, will be the last lecture that we have on the proof, and after that and after next Tuesday, we no longer see each other in Zoom. Remember, next Tuesday will be gonna be the last date meeting that we see each other in Zoom. Of course, I would take attendance. So why should I take attendance? Because I believe that we have some people who miss 1 or 2 absences. So you don't want to be that as part of your grade. So I might take attendance on next Tuesday. If you still feel like, well, I need more grade on the attendance, I can come. I can come on Thursday and take attendance one more time before we take the exam. I feel like that's going to be fair, so that your 1 or 2 absences not going to be play a huge part of your grade. So I feel like next Thursday I can take attendance as well, and then you guys can take the exam. Again, that's going to be the same format as the midterm, so that'd be 2 hours and 30 minutes for that. If you need accommodation, or you show me a letter for that, you can have another uh, uh, additional 1 hour. Yes, absolutely. So make sure that you're gonna do so. But I'm not gonna be lenient or final exam that before you submit. And please do me a favor, double check the file if you miss any of them, or if you miss them. But please um, remind me by email by sending me within that hour. So cannot be like beyond more than 5 hours. So I still now I remember I forgot to send you a few files, but for the midterm, I'm very lenient with that. So again, that the final exam will be covering from lecture 7 up to 11, right? So we do not have homework 6. We do not have lecture 6. And there were some people asking me about the homework problem. Will I be graded? The answer is the absolute yes. So you will be graded based upon the homework that you submitted, either by email. So don't worry if you submit it by email and you saw it for like you did not submit it, but please try to do it on Blackboard, because I might lost your file. I might have lost your file if I double check them. Maybe I did not check it for like 2 weeks or something like that. So it's always good to submit in Blackboard rather than by email. Send it to my email is gonna be something is really weird. So we actually finished lecture 9, but since we haven't really got to the thing that we have, and then we're gonna repeat what we're trying to prove for lecture 9. So I think I should take attendance on that day right now. Let's see. Okay, so the direct proof is something that we just prove it. Let's say P and imply Q, right? So this is what we call direct proof, that we did that last class. So this is what we call direct proof. So we prove it directly. There's no trick behind that. I'm using information, use P information to prove Q. I mean, this basically the strategy that we apply for that part. So I can give you a few proof, for example, that any number. So I can give you this question on the exam. The sum, if the sum of the digit of a number is divisible by 3, then that number is also divisible by 3, right? So it's almost like even then. Literally, I give you some information of the P, and then you prove the Q. It's obvious. So this is the part that then the number is also divisible by divided by 3. Simply put. So it seems to be like a little bit headache for us. So you can check them. Let's say we take 4, 5, 2. Just give me any number for that part, right? So just give me any number for that part. Let's say 4, 5, 7, 8, 1, 2, 6, 7, 9, and 5, for example. So this is just the way we check them. I just pick a random number. I just want to see. I want to prove if the statement is correct or not correct. And so we're using the information that we have, the conditional statement telling us that if the sum of the digits of a numbers divide by 3, then that number is also divide by 3. No, not by 9. So yeah, I mean, this is just a little trick that I show you. There's nothing, but it's better to learn something new that we did not learn from high school, maybe middle school, right? So let's say I give you that digit, and would you be able to tell me if that digit is also divisible by 9? I'm sorry, divisible by 3? Yeah, it worked for 9 as well. So if the sum of digit of a number divide by 9, then that number is also divided by 9. So that's pretty obvious. It's pretty much the same statement. I did not really work another statement saying, well, if the digit
divisible by 9, then it's, of course it has to be divisible by 3. It's pretty obvious for us, but just the sum. So we're going to take that. So 4 plus 5 plus 7 plus 8 plus 1 plus 2 plus 6 plus 7, and so on and so forth, plus 9 plus 5, right? So again, this class is we focus on the critical thinking and how we can improve the logic. It's, you know, it's not about the material that we learn. Of course, that we learn how to prove this, but the most important thing is we want to be able to be aware of the logical reasoning that we have picked up. Just like we take the philosophy classes, that we develop the critical thinking skill is more important than solving a problem. But anyhow, we have 4 plus 5 plus 7 plus 8. So I'm going to use my calculator. I think I can do it, but I haven't seen people using my calculator that I show you. I feel like it's gonna be a waste, and we can do so. Of course, I made up these digits. I should be able to divide by 9. Let's see what's going on. I'm sorry, by 3. So let's try it out this one. So we take 4 plus 5 plus 7 plus 8 plus 1 plus 2 plus 6 plus 7 plus 9 plus 5. And 54, so we know the fact that this digit, so 54, it also divide by 9 as well, but by 3 first, and you got 16. 18, that's perfect, right? So that's perfect. So so the sum of the digit, I add them up, and I got 18. It worked perfectly well. And I take the digit, let's say 4, 5, 7, 8, 1, 2, 6, 7, 9, 5. I divide it by 3. I also get sum of the digit like that. Of course, it's divisible by 3. Actually, divisible by 9 as well. So when I divide it, because 54 divided by 9 is also 6, right? So it worked for the sum of digit of a number divisible by 9, and a number also divisible by 9. The sum of digit of numbers is also divisible by 3, so then the number is also divisible by 3. Yeah. So this is the thing that I'm not sure if you guys learn it, right? And so this is a very, very basic strategy that we have right there. But I'm not asking you to prove this. The proof wasn't that bad, but we have to the digit. Let's say we take, how many digits do we have? Let's say we have 9-digit numbers and whatever it is, and then we're gonna form them as, you know, A1, A2, A3 up to A9, and then we're gonna rewrite them. So let's say we have like a 3-digit number. Let's say we have 3, 4, 5, for example, right? So 3, 4, 5. Apparently that we no, this is not we trying to have that. I should not give you this proof on the exam. It's basically too tough. So you can rewrite them, right? Something like that. 300 plus 40 plus 5, so there were 3, 4, 5. And when I add them up, 3 plus 4 plus 5 is 12. 12 over 3 is also divisible by 3. So 3, 4, 5 absolutely have to be divisible by 3. Apparently, the answer is 115, but this is not the case. I forgot to put them down. So 4, 5, 7, 8, 1, 2, 6, 7, 9, 5. Did I type them? It's also divisible by 3. Well, I mean, I have a lot of trick, but you know, we don't have a lot of time to do in the summer. Usually the spring and the fall semester, I show people trick, a lot of trick. It's not the trick, it's just how we realize the pattern behind the numbers. And you see that it's pretty fantastic to do so. And so on and so forth. And we can also have this, right? And So we can rewrite any 3-digit number in terms of 3 times 100 plus 4 times 10 and plus 5 times 1, for example. And then we do that the same thing, and then we prove it along the way that that's not going to be a big deal. And I can also rewrite this as no, I'm not trying to prove, this is not general case to prove it. It's just like so we can have like a 3 times 100 plus 4 times 10 plus 5, and so so we're gonna have like a 3 times 99 plus 4 times 9 and plus 3 plus 4 plus 5, right? So, and of course, this guy divisible by 3 for sure, right? Divisible by 3. And so if those 3 numbers divisible by 3, and of course the whole digit is also divisible by 3. So it is not the proof, it's just showing you that we can rewrite any digit number in terms of the first digit times 999, it depending on how many digits that we have. So let's say we have like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that'll be 4 times 999 plus 5 times 999 plus 7, whatever it is. And keep going. And then we're going to end up getting the last digit 4, 5, 7, 8 plus 2 plus 6, 7 plus 9 plus 5. And if we add them up, those digits divisible by 3. And of course, it's also divisible by 3. This is just the common sense that we have right there, but I do not offer you a general proof for that part. So let's go out of the script, the lecture, but it's pretty good to see them. Same thing for that. It was sum of digit divisible by 9, so then that digit is also divisible by 9. So for example, I can have like so 1, 2, 3, 4, 5, 9. So it just add them up. So you get 9, 6. Right, so this is 4 plus 5, 9, and 9 and 6, and it's 3. So when they divide it by 9, yes, the answer is absolutely yes. Right, so you just add up the digit, we got 27, and so of course this digit is also divisible by 9 for sure. But it is just the general information that we have right there. So the next proof that we have, we call the contrapositive proof. So that would be a not Q. Remember that we cannot use not P. We cannot use negation of conditional statement to prove negation of the resulting statement. So we need to take the result statement first. So negate that and prove the other one. So this is not Q and proving not P. Okay, so what that means, this is what we call contrapositive proof. Use negations of Q information, of Q, of info, negation of Q to disprove P. Anyway, so to disprove it, meaning that we try to prove it wrong. If in other words, that'll be the next part of that we're going to study. So we call it contradiction for this part. Okay, so remember that those two are basically the same. So proving P imply Q basically means the same as P imply Q. That will be the same. So the same, I'm not saying the same, I would say they're equivalent to each other. So I have to put the equivalent size for that part will be the same as not Q and imply not P, right? So they are basically the same because they form the same logic table for that part. So this is the thing that we have right there. So now we're gonna go to a certain example and see how we can proceed that. So so this is the lecture. I think we stop at a certain point, and are we gonna do like a few questions? You can pick any question that you want. It's not a big deal to do so, but it's really good to see what it is. Right, we're gonna do some basic information, and then see how we're gonna proceed that. Right, and so I'm not gonna write down the questions. I'm gonna copy and paste, and just want to be saving time. So this is the question number 3 that we have on the worksheet, and show the following using contrapositive proof using cases. So we should be able to understand and highlight the important facts. This is the review sheet will be uploaded on Thursday. Yeah. So, and after that, I'm gonna post solutions after Tuesday. So this is the P, and this is the Q, right? So the P is phi not divided by xy, then phi not divided by x, and phi not divided by y. That's pretty obvious, but we need to prove that part using contrapositive proof, right? Contrapositive. So you need to tell me on the exam, state clearly what kind of proof that we do, or sometimes I ask people to do so, right? And apparently that this is, we're trying to prove not Q and imply not P. We need to do the opposite for that, right? So not Q imply not P, okay? So this is P imply Q. So the way that we prove it is pretty obvious that we're gonna take, we need to take negation of Q in this case, so that would be phi divided by x, right? This is a very important thing that most people actually make mistakes on the exam, that if this is the and, so negation of the Q should be the or, right? So it's not the and anymore. It has to be or, phi divided by y. So it doesn't work for both of them when we try to negate the Q on the statement. So case 1, so either phi divided by x or phi divided by y, and then we can split them into two cases. So phi divide x, right? So meaning what? Phi divide x, so I can rewrite x equal to phi times k, right? Phi times k. So it's where my k is basically an integer, so it can be either positive or negative. So where my k is literally in z. Well, I mean, this is not a z that I'm looking for. It should be the z that we have right there, right? So this is the whole set of the whole numbers or the integers. So the letter z should be this. I wrote it wrong because I don't have this letter on my keyboard, right? So if phi divide x, and then I can rewrite x equal to phi times k. So so what that means is that I can multiply x times y, right? So x times y would be equal to y times phi k times y, which is phi times ky. Yeah. And of course that if I can rewrite xy in terms of phi times ky, I call this as you know, z, I'm sorry, we're not going to use z, p, whatever it is, or q, right? So meaning that I can rewrite this as phi q. So phi q meaning what? X, y also divided by 5 generally. So we can just put them down. X, y can divide by 5, right? So so we finished for case 1, and K2 basically the same thing. K2 where phi divided by y, right? So either one of them, meaning that I can rewrite y in terms of phi times. So instead of k, I use m, right? And so meaning that m is literally in z. Okay. And it's basically the same thing without loss of generality. So I can rewrite xy, x times y would be equal to phi m times x, right? And so because y in terms of phi m, and I can pull out a 5, and then I multiply x and m together, and I call this as q, no, m, whatever it is, it doesn't matter, right? And so this is phi m, meaning that phi also divided by xy. So we done. So again, that when the questions and when we convert, a very important thing, if the q has the n, and then we need to negate that, which is or, and then we have to split that into case by cases so they can finish the proof. Okay, so this small question shouldn't cost a lot of time to do so. So I would like to do a few more questions. I would say do question number um, 1 and 2 and see how we can proceed that. I feel like 1, 2, and 3 are very important. I might give you these questions as edge credit questions, and it's easy, but you don't have to, spend a lot of time proving it. Just logically explaining to me, you don't, why is correct, why is not correct. So I'm gonna prove this and see how it's go. So what we have right there was the integers, right? And so the P and Q was the following thing. So this is P and this is Q, right? So proving n squared is even, then n is even. That is not easy where n is in integers, right? Suppose n is an integer. This is also very important information, right? So if we want you to use direct proof, right? So it's possible, but it's just tough to do so. Why it is harder to use direct proof than the thing that we have? The reason behind that, because let's say n squared is even. So n squared is even, so I can rewrite n squared in terms of 2k, right? 2k. 2k, where my k is in integers, is in z. So that's pretty obvious that we can use that information to prove it, but it's not easy. Why is not easy? Because so I'm trying to solve for n, so I ignore the negative part. So n would be equal to radical 2k. We ignore the negative 2k, right? Okay. But we know the fact that k is n is integers, right? So we know the fact that n is literally is in integers. So meaning that radical 2k will also be in integers, okay? So of course, But the only way that can make this guy is in integers is that k have to be a factor of radical 2 something, right? So meaning that k have to be a factor of radical 2 times p, okay? P squared, in other words. So when we take that, just want to make sure that it have to be an integers for this part, because there's no way you can make that. We can't. How is that possible? You can make radical radical 2k's an integer. So you can plug in k equal to what you're gonna make that will be an integers, right? So this is not easy. So k can be 2. Can it be 4? No, right? So k cannot be 4. But k can be 8, and so on and so forth. So you have to be the radical 2 something, p squared, in order to make that as an integers. And so that being said, so k have to be in terms of that, and then we can have this guy, which is 2 times 4p squared, which is 2 times, so this guy I'm going to replace by 2p squared, and 2 times 2, which is 4p squared, and we can have this as 2p generally, finally. I mean, this is a pretty high logical reasoning for that part. And so this is what we call for the n, and this is the n equal to 2p finally. And we prove that, so p is even, then we're done, right? But using the direct proof to do so, especially when we're dealing with the radicand, that is not an easy task, right? So we need to use the logical reasoning that if n squared is equal to 2k, because n squared is even, then n have to be radical 2k, and then we know the fact that n's have to be the whole numbers. Then radical 2k also have to be a whole number for that. But the only logical thing, the only way that we can make radical 2k as a whole number is when k is actually have to be in terms of radical 2 times the perfect square of a number. And we plug that in, and then we can solve for the n, which is radical 4p squared, and then equal to 2p. But this is not an easy proof for us, especially when we dealing with a very, very complicated system. And the better way that we can do so is when we use contrapositive proof. It's going to save it a lot of time and a lot of work. All right, contrapositive proof. What is the contrapositive proof that we're trying to do so in this case? So this is what we need to be doing, and this is what we need to work on. So not p, right? So it's not q. And what we're trying to prove will be the not p, okay? So we're trying to prove not p. So the way that we're trying to do so is, so q is, n is even, so not q, so n is not even, so n is odd, right? And we can rewrite n in terms of n equal to 2k plus 1. Right? And so remember, this is completely different from the question that we have, from the proof that we have earlier. So it doesn't matter for that part. And we can say k is literally z. Okay, so what we're trying to do, we're trying to prove that n squared is not even if n is not even. It's as simple as that. So for that part, I can rewrite n squared in terms of, so we're gonna rewrite n squared in terms of the 2n plus 1 square, right? 2k, I'm sorry about that, 2k plus 1 square, because n is 2k plus 1, right? And we can expand that. Again, you can use any strategy that you explain. You can use binomial coefficients and so on and so forth. But I'm not gonna spend too much time working on it. So you can use the form method, whatever it is, but I'm just going to expand it in one line. So that'll be 4k squared plus 4k plus 1. Okay. So so this part I can also factor 2 out. When I factor 2 out, I'm gonna have this guy, which is 2k square plus 2k plus 1. And plus 1. So apparently that this is 2p. I call this as p. We can have 2p plus 1. We're done. So we're trying to disprove the fact that n squared is not even, meaning that n squared is odd. So meaning that you have n squared is odd, we're done. So the next part of the question was a same thing. So if a squared times b squared minus 2b is odd, then a and b are odd. So using direct proof is actually really tragic, because we can write a squared times b squared minus 2b is odd, right? So let's consider direct proof. When you see the conditional statement is complicated, please do not use that. So we can multiply them, and we can have a squared times b squared minus 2a squared b is odd. So meaning that this guy have to be 2n plus 1. Okay, so if this is, so 2a squared times b's have to be even. So if this guy is even, then so a squared times b squared have to be odd, because we can add 2a squared b both sides, and then factor 2 out, and so on and so forth. So we can have a squared times b squared is odd. So that had to be equal to 2, let's say 2k plus 1. So k would be an integer, where my k would be n plus a squared times b. Okay, and so if a squared times b squared is odd, meaning that they have to be odd. Both of them have to be odd, right? So because when you multiply them, so if one of them is even, then we do not have the odd numbers. So both of them have to be odd. So both a and b are odd. But it is not easy to prove it, because we need to convince me why, if we multiply the square of a number with another square of a number, so how do we know that the product is odd, meaning that those two numbers have to be odd. So this is not an easy proof for us. And so the way that we're going to prove it is we're going to use contrapositive proof for that part. So contrapositive proof is something that we can utilize the informations. So in this case, we're going to rewrite a and b are odd, meaning that a is odd or b is odd, or b is odd, right? And so we need to split up into cases, but this one is a lot easier than the from the previous example. So cases, case one, a is odd and b is even, right? And we can also prove that by saying that so when a would be equal to 2k plus 1 and b equal to 2p plus 1, okay? I'm sorry, 2p, I'm sorry about that. So that we can prove that the thing that we have earlier would be a squared times b squared minus 2b is not odd. So we can have a square times b squared minus 2b so we can expand it, so that'll be 2k plus 1 square times b squared, which is 4p squared, and minus 2b, so that would be 2b. So b will be 2p, so 2b would be 4p, right? And apparently we can check them by, we can expand it and so on and so forth, and you're gonna get a certain thing that this integers will be an even, right? So this have to be even numbers, because I can factor out 2, I can factor 2 out in this case, so I factor 2 times 2k plus 1. And square, and times 2p squared minus 2p. So given by that, we can have this as, we can call this guy as q, right? So this will be 2q, meaning that this guy has to be even. Okay, so which is even. Contradiction. So we're done. Right? So because the statement saying if a square, so we're trying to prove that this guy is not odd, which is even. And similarly, that we can use in that case. Similarly, we can do that for case 2. Similarly, for case 2, A is even and B is odd. So that both of them cannot be odd at the same time. So this is where the case is. So A is odd, or B is even, or A is even, and B is odd. I think we need to do both of them as odd as well, and see. And then for case 3, A is, let me just check them again. A and B are even, and B are even. Both of them are even, so apparently that we can prove it, which is A squared times B squared minus 2p. So if both of them are even numbers, then we can also do that. So both of them are even, so we can have A equal to 2m, where my m is z. And B will be equal to n, where my n is in z. Okay, so we can also replace that for 4n squared times, so b squared will be 4n squared, right? And minus 2b, so 2b, so 2 times b, which is 2 times 2n, so that'll be 4n. Apparently that can be write this as 2h, where my h is equal to whatever it is. So we factor 2 out, so this guy has to be even. So we're done for that part. Now we're gonna see how we're gonna deal with this, the last John writes on his exam. Yeah, this is a pretty good part of the questions. I might give extra credit for that. So do you think this is the logical reasoning that we have, right? So think of it. John writes on his exam, the function f of x equal to x squared is continuous at x equal to 0. Therefore, it is differentiable at x equal to 0. Is that a correct reasoning? Why and why not? Right? So this is the thing that we might want to consider for that part. So continuous, does continuous imply differentiable? Right? So we know the fact that, so this is not a correct reasoning. This is not a correct reasoning, right? And you can say that as well, and you can explain it why this is not a correct reasoning for that part, because continuous doesn't imply differentiable, and but the other way around should be work. So, for example, I changed the wording for that. The function f of x equal to x squared is differentiable as x equal to 0, and it has to be continuous as x equal to 0. That is correct, because of what? Because continuous, the continuity does not imply differentiability, right? And so Nietzsche explained to by saying that f of x is not differentiable because in other words, so you can say f of x is not differentiable at x equal to 0 does not imply that f of x is not continuous at x equal to 0. So this is the thing that we you need to use a certain thing, a certain like a logic, just to show that. So this is not true, right? So there are certain function that we have learned. If not differentiable, it's still continuous for that part. We have x equal to absolute values, right? So it doesn't work for that statements, but let's say y f of x is equal to absolute value. So apparently this guy is differentiable, but I'm sorry, this guy is continuous at x equal to 0, but it's not differentiable at x equal to 0, right? So, but it's all continuous. So it does not satisfy on that statement for that reason. So when you have a piecewise function, even if it's continuous, but it's not differentiable, for example. So we have a certain example for that part. So you can basically see that the piecewise function is not differentiable at x equal to 1. Why is that? Because the limit for x go to the left side when x equal to 1 does not equal to that, right? Does not equal to the right side limit, and so we can't say that they are differentiable. So we can work on these questions. I feel it's sometimes it's kind of fun, just kind of interesting to know. But of course, we do not need to know them all. We just need to know part of it, right? So remember that sometimes we need to use the contrapositive statement to disprove there's no way that it's to use direct proof, or maybe it's just overcomplicated. So the best strategy is sometimes to solve the statement using the contrapositive proof for that part. So we can't say that. So how can we know this is not continuous at x equal to 2? Okay. So how can we use the contrapositive statement to show that this one doesn't necessarily have to be So because f of x is not defined at x equal to 2, right? Then f of x is not continuous. I feel like that this guy doesn't have to be like that at x equal to 2. Okay, but for this part, show that this guy is not differentiable at x equal to 1, meaning that we're going to take the limit of f of x when x go to 1 minus. So we can see that when x go to 1 minus, then you have to use the top functions. So that would be the limit of f of x, which is x squared. So we're gonna plug that in where x go to 1 on the left side. So we can see that this guy is equal to 1, and the limit of the same functions. Remember, this is the piecewise functions, so it might have a different period, different point where the function varies along the way. And if we go to the right side of the 1, and you can see that the function that we need to evaluate the limit where this is equal to 3x. And so when x go to 1 on the right, so basically the function is literally equal to 3. So they have different limits for that part. So limit of f of x when x go to 1 minus is different from the limits of f of x when x go to 1 plus. So so it's not, so the derivative does not exist, right? Does not exist at x equal to 1. Even if it's perfectly continuous, when you draw the picture, it should go like this. So for that part of the reason. So x squared is literally something that we can see right there. Okay. Whatever it is, right? And this is 1 and 1. And the 3, so it should be right there. Whatever. It's open circle because it does not exist for that part, and you can see that. So the limit on the left side should be different from the limit on the right side, and apparently that we do not have the same values of the limit part, so it does not exist. It's not even continuous for that part. Anyhow, we finished this, and we're gonna start the new lecture very soon for that part and see how it's go. Okay. So let me check them. All right. So now we're gonna go to the next part of it. Yeah. So this is the worksheet for that part, and how we're gonna prove the contradiction. So what it means by contradictions, we're gonna go over the concept relatively quickly for that part, and we're gonna focus on what it is, right? So the contradiction is something that we trying to prove it by contradiction, trying to assume something wrong, and then we prove that. And there are infinitely many prime numbers, and this is also one proof that we can check it on a Blackboard. And if we want to prove any statement for that part, and we need to assume something is wrong. right? And then, and then we go the opposite for that part. And then we're gonna prove this is contradictory for that, and so on and so forth. Okay. And so the thing that we're going to be doing, prove by contradictions. Okay. By contradictions. Assume that something is wrong. And then we disprove it. By contradiction generally. But for the statement, that should be a different story for that, right? So we can read those lectures and see what it is. And you want to prove that for every positive number of x, and we're gonna have this. So let's go copy and paste and show that using contradictions and see how it turns out to be. Okay. I cannot copy this for some reason. All right, so let's show this. Okay. So assume this is wrong. Assume this is wrong. Assume that this is wrong. Oh, this is false. So some of you might be getting used to the word false rather than wrong, so you can take that. And so meaning that we have x over x plus 1 is greater than x plus 1 times over x plus 2. So I apologize for my handwriting for that part. So this is x plus 1 over plus x plus 2. So remember that we need to take the opposite for less than. So that should be greater or equal to, assuming that for every positive real number x, so meaning x greater than 0. So remember that we cannot just forget any clue that the question gives. Real numbers, x greater than 0 and x is r, right? So now we're going to multiply both sides by, we're going to use the cross multiply. So you need to multiply this with x plus 2 and multiply that with x plus 1. And we can have, this guy will be x times x plus 2 plus and greater than or equal to x plus 1 times x plus 1. Okay. So that being said, that we just use the cross multiply, that we're gonna take that, and we should be able to get it done, right? So we're gonna use the cross. Why can we use the cross multiply and without changing the sign? Because x is positive, right? So if x is not positive, then we cannot do it that way. So and then we can expand it using distributive and Fourier method, whatever you want, and so we're gonna have x squared plus 2x and greater than x squared plus 2x plus 1. So we subtract x squared plus 2x both sides, and we subtract x squared, and we subtract 2x, right? So we subtract x squared and 2x both sides. So we can see that 0 is greater than 1 or equal to 1. That is the contradiction, right? This is false, a contradiction. Okay, so we're done for that part. This is false. Okay, so we do not really have to worry about that. Actually, it shows you basically exactly the same way that it did. Okay, so there's nothing really problematic for that. Okay, so again, that if the questions only gives us the statement like that, without any conditional statement that we've done, which is prove or disprove that. But it's probably not going to be on the exam because we do not have this. Okay. Now we're going to go to prove by contradictions for conditional statement, right? So meaning that it have to be if, and then. So I just want to remind people that something that we have before. So if P, then Q, for example, then Q. Okay. So again, that we can rewrite this P imply Q, correct? So this is what we call the conditional statement. But in order to use the contradiction then, so P imply Q, so that gotta be the same. I mean, it's not gonna be the same, but they are equivalent to what? To be P and not Q, and very important. And pretty much using the P informations, use the P info and not Q info to disprove, to show that this is contradiction. To show the statement, the contradiction. Okay, so that would be a thing that we have right there. Okay. You can check them out, the work part. Yeah, this is P and not Q, okay? Actually proving this wrong. I apologize for that. So this is not, I think I'm missing this sign for some reason, okay? So not P and not P imply Q will be not Q imply not P, okay? So basically the thing, okay. So the thing that we're going to be working on, we're using the P information and not Q, and so this is and, right? This is and informations, and we're going to use that information to prove a certain part of it, which will be the following thing. So we're going to take a look at that and see. We're going to do like a maybe 2 problem, and pretty much I will let you go for that part. Okay, so we're gonna do 2 and 3 and see how this turns out to be. Oops, I think I just misclicked that. 2 and 3. Okay, and then we're gonna take attendance, and we're gonna have some review on Thursday for lecture 10, and finish induction on that day as well. So Thursday gonna be a lot of work, and then we're gonna go over certain questions for exam review and do the exam review in the next Tuesday, and Thursday will be the final exam. So so this is P, right? So this is P, and imply this is Q. Okay. So prove by contradictions, meaning that we're going to take prove and not Q. Okay. We're going to take the informations, meaning that what is the P and not Q that we need to assume? We need to assume that A squared is even, then and A is not even. So A squared is even and A is not even, okay? Not Q, so Q is A is even, and not Q will be A is not even. So A squared is even something that we learn it. So now we're gonna do the next part of it. Let me just write them there. So this is the P, right? So P, we don't change the P for that. We're trying to contradict the P with the not Q. Basically similar to the contrapositive proof, except for the fact that we use different syntax for that and prove for the contradiction part. So A is not even, then A is odd, and A equal to 2K plus 1. Okay? So we can rewrite A square. We try to contradict the P. So A square will be what? Will be 2K plus 1 square. And so we can also write them down as 4K square plus 4K plus 1. So that gonna be, I'm gonna factor out 2 so that I can have the 2 something plus 1. 2K square plus, so I factor out 2 for this part, and we're gonna get 2 times 2K squared plus 2K and plus 1. Where my, so this would be equal to 2P plus 1, where my P is 2K squared plus 2K. So this is odd. So A squared is odd. Okay. So which is the contradiction? Because we assume that A squared is even and A is not even. So this which is the contradiction. So the statement have to be correct. So the statement, then we conclude that, so the statement is true. Okay, so similarly that we have a certain thing, so the P and Q, P that we have is A and B is in Z, and A is greater than 2, and we have Q that we have is A divide B, or A is not divided by B plus. I think this was similar to the thing that we have. So so we're gonna contradictions prove that we're gonna show that again that would be P and not Q, right? So P and not Q. So what is the P? So P will be A, B, assume we need to say that before we can write out anything. So assume A, B in Z, and A greater than 2 or equal to 2. Right? So N, so we need to have N in this part. It's really important. And we have what we have. So we need to take the contradictory for that part. So we're gonna take the A divide B, and A also divide B plus 1, right? Okay, so we have to assume that. So A divide B, so we can also say A divide B. So we can have B equal to KA. Okay, and also A divided by B plus 1. Meaning that, so B plus 1, which is also equal to, so we cannot use K, we need to use M. times A. All right, and then we subtract them for this part. We subtract B equal to KA and B plus 1 equal to MA, and we can have, we subtract them. So we take B plus 1 minus B, so we're going to get A 1, right? So we take B plus 1 minus B, basically the same as MA minus KA. So I factor A out. So once I factor A out, I'm going to get M minus K. Right? So remember that we just subtract B plus 1 to B minus 1. You subtract, this is 1 and this is 2. I call 1 and 2, right? So we take 2 minus 1, right? And then we can have this. Okay, and I factor A out. I'm going to have I factor A out, I'm going to have M minus K, where M and K is basically integer. Remember, M and K have to be in integers. So should be bigger than 1 for sure, right? So it cannot be like a, you know, they have to be different, right? So so M minus K, so M minus K should be greater than 1. This guy should be greater than 1 for sure. Right? So M is integers, K is an integer, so this guy have to be greater than 1. And I divide both sides by M minus K. Remember, M and K are just the multiple of A is nothing else, right? So it can be, M can be equal to 100 and K can be negative 20. It doesn't matter, right? So it's just the random multiple or random numbers for that part, but have to be greater than 1 for sure, and because of that. So it doesn't look like the thing that we have right there, but anyhow, we're gonna have to rewrite this. So, and then we cost amount this, and so we're gonna have divide both sides by M minus K, so we're gonna get A equal to 1 over M minus K. So we know the fact that M minus K greater than 1, so this should be less than 1 for sure, 100%. 1 or negative 1s, okay? 1 or negative 1s for that part. So anyhow, so assuming that M is greater than K as well, just want to make sure that we have this, okay? So if this guy less than 1, how is that possible? A is greater than 2, so this is the contradictions. Because we assume that A is greater than 2. So this is the contradictions, which is the contradictions. And then we're gonna write them down. So then the statement is true for that reason. Okay, so generally we've basically almost finished. I think he did the same thing for that part, but we're using different format for that. D minus is positive. Yeah, it's basically the same thing. It should be less than true for sure. Actually less than 1 for that reason. And so you can read the staff and see basically the same proof for that part, but we just use different note for that reasons. But anyhow, so this is the thing that we finished. So now what we have to do next, we're gonna take attendance. No, we're gonna do one more example before we go for that part, because we need to finish that. So finally, so prove that the prove that the an is odd, then n squared is odd, right? So if we use direct proof, that's easy, right? So just use the OU contradiction, the same thing. But we're gonna assume that n is odd, then n squared is not odd, and then we're gonna do that. But it's actually more complicated. Use contradictions, okay? And for this part, we have to assume a and b are integers, then we need to show that a squared minus 4b minus 3 is not equal to 0. And the logic behind that is because a squared is odd and a is odd, and so we cannot have that. When we have the odd number, we subtract the integers, and the even numbers, so 4b would be an even number for that part. And so we cannot, the thing that we have right there. So we can try to do question number 2. I feel like question 2 is pretty complicated, but let's do it for that part. So we assume that we have a squared. So assume that a squared is odd, then a is odd. So this is, I would say, for that part. We did that earlier. So we're gonna try it for this part. So let's say a squared, assuming that, so prove by contradictions. I'm gonna take that and prove by contradictions. And p and not q, right? And not q for that part. So where my p is this, right? This is the p. And this is the q. And we're trying to show that the p and not q. So we're trying to show that this is not an integer. So we can take a squared minus 4b minus 3 equal to 0, right? So not equal to 0, so not q will be equal to 0 for that part, right? And so we can have this guy, which is we can literally just add 4b and 3 both sides. We can have a squared, which is equal to 4b plus 3. Okay. And for that part, we trying to look for the a squared, which is equal to 2 times 2b plus 1. Okay. Right. And so for that part, is a and b have to be an integer. So a squared equal to 2b 4b plus 3. That'll be 2 times 2b plus 1 plus 1. So this one, a squared is odd, right? So a squared is odd, then a is odd. Okay. So if a is odd, then we can also pretty much a thing that we can write them down as a squared is odd, then a is also odd. And so the proof in this case is we can have a which is equal to let's say equal to that's obvious for that part, but and so for this part, so we can try certain things. So let's say b equal to 1, then 2, 3. So this is obviously that we have here. So a squared equal to 2 times 2b plus 1 plus 1. So a's would be equal to 2m plus 1, for example. And then we play around with that. We plug that in. So we plug in a equal to 2m plus 1. And then we're gonna basically we plug that in 2m plus 1, and we show that there's no b. That's satisfying b is a positive integers. So meaning that we're going to plug in a equal to 2m plus 1 into this again. Okay, so we're going to have the information which is 2m plus 1, because m also will be an integers. Because a squared is odd, then a has to be odd. Minus 4b minus 3 equal to 0. So we can see that there's no b that satisfies the whole integer for that. So, and then we're gonna expand this, so that'll be 4m squared plus 4m plus 1 minus 4b and minus 3 equal to 0. Okay, so we divide both sides by 4. I'm gonna get b equal to divide both sides by 4. I solve for b, just solve for b for that. So 4b would be equal to 4m squared. This one is pretty complicated questions. Plus 4m minus 2. Okay, so we just add 4b both sides and take 1 minus 3, which is minus 2. And then I divide both sides by 4. And I got b equal to m squared. Remember, m is an integer for that part. Okay, so plus m minus 1/2. So this is not in z for sure, right? Because this has to be a fraction. This has to be a fraction. So so it's contradiction, because we assume that a and b are in z, right? And a squared plus 4b minus 3 equal to 0. But this doesn't work for that part. Because we use the information to prove that a squared is odd. And we take the a squared is odd to show that a is odd. And after that, I use information to prove that b is not in integers. But we assume what we assume, we assume that a, b are integer for that part. So this is contradiction, right? Because we have the m squared plus m minus 1/2 is not in integers at all. So which is contradictions. Okay. So so then the statement is true. Okay. So this is the thing that this pretty complicated question, to be completely honest. But it's the same thing for that point. There's definitely not going to be something good. So we're going to do this question. So this is not the conditional statement. So, oh no, yeah, it does. It is. So Ab and Ben, I'm sorry for that. So f of x equal to 2x plus 3 over x plus 2. Then, so we assume this is f of x equal to that. And f of x is, then for every x in R, f of x is different from 2. So we just need to rewrite them. And f of x is equal to 2. What happened is that we're going to have 2, and then we plug that in, and we see that 4 is we're gonna see the contradiction for that part, right? And you can literally check that. It's pretty straightforward. But we're gonna do this one on Thursday, and then after that we're gonna jump to lecture 11 and the exam review, and after that we're gonna spend the entire lectures on next Tuesday to work on the exam review. Okay, so I feel like that's gonna be it. And I would like to take attendance and remember that we can watch those lecture again on Blackboard for that part. So just want to make sure that we have the attendance for today. And if you can type in first in order for Lantina, and that would be great. So here, this part is present. Richards, okay, gyros here? Gyros here? Yes, absolutely. And I saw that sometime. My message, my eyes is Kenneth is also here, and Cisse is here, Paulina is here, Brenner is here, Laura's here. Okay. Okay, that would be great. So I'm going to check an email. So for those of you, please, if you don't see your midterm grade, please email me. Or maybe you just double check the email. I actually sent out an email last Thursday, but not very few response. Lauren's here, and Hannah's here. Kenneth is here. Well, that's fine. It's not a big deal. We have an emergency time as well. Yeah, sometimes we go, maybe I have to curb my dog a little bit when teaching, but they're all slipping for that part, which is really cool. Mackenzie is here. Coddy's here. Okay, Kim is here. Again, that if you get more than 100 on the exam, I mean, the point is there. I do not write out to 100. It's still count to the final grade. So why don't we try to do the extra credit part for that, right? So some of you skip them. I don't know why, but just 2 points telling me why you are interested in my class, learning this, and another 5 points to answer the questions. John is here. Absolutely. So Yvonne's is here. Milano is here. And Oriental is here, right? So I saw Patricia's is here. I think I'm not sure. Let me just call some people who actually didn't have the grade. I graded almost every one of you, but there were some people who did not really get the grade because you missed the questions. And I can grade them. I can just literally give 0 on those questions, but I don't want to. So yeah, it was here. Art is here, and also Art. Your homework should be counted, so you know that the. But you have to send me for that part as well. Yeah, Linda is here, and Ariel is here. Mohammed is here. Jonathan is here. Sani, Mimi, and Winnie. So Winnie's here. You need to send me the file of the exam. I can't read it on Blackboard. Yeah. Oh, okay. So that would be great. So I'm gonna see them. For those of you who didn't have the grade, I need to see them for that. Yeah. So that it kind of feel like remember that the file should be something that I can read. So if I can't read them, please try. Mimi is also here. And Winnie, fantastic for that. Remember that we have any trouble with the attendance, let me know for that part. So if you registered late, meaning that I do not take away point for the first week that you did not come to the class because of registration. But if you are here, then you have to be present for that part. So anyhow, I believe everything is good. If you don't see your attendance, better let me know. And I hope you guys are going to enjoy your day. See you guys back on Thursday, and take care.